Now we will be working on homework 10, the last problem about the set, reset, flip-flops. I already did a little bit of preliminary drawing on here just to kind of get started. But so maybe from class, I'm not sure what you guys have done so far. It says, in class we showed you how a set, reset, flip-flop could be made from two cross-coupled NOR gates. You can also make a set, reset, flip-flop from two cross-coupled NAND gates as shown below. So you can see here that we have our flip-flop, and it says analyze the circuit and complete the truth table above that describes what happens to Q for each of the combinations of A and B. The choices are set, reset, hold, and illegal. So that means that in these spots in the truth table, you will be writing set, reset, hold, and illegal in some order depending on what those different combinations do. And so down here, I also drew the truth table for a NAND gate. Let's mark that in red. This is just so we will be able to reference it while we are working on the problem. And I also wrote down what set does and reset does. So if we get to set, set will make Q a 1, as well as reset will make Q a 0. So if we see those things, we can assume that those are set and reset. And then what hold does is hold, it just maintains whatever Q is. So if Q is a 1, so I'll use Q sub 1, then Q stays Q sub 1. If Q is a 0, then Q stays Q sub 0. So there will be one of the different combinations of A and B. It won't change anything. As well as illegal. Sorry about L-E-G-A-O. So illegal is when the outputs. So what we notice is that our outputs up here are Q and Q naught. So if we ever get Q is equal to Q naught, that means we've reached the illegal state. And we'll talk about that one when we get there. But basically, if the outputs are the same, that means that our setup is not correct because we define these to be opposites of each other. So let's start by putting in some inputs into our circuit. So let's start with A is a 1 and B is a 0. So now some of you might be wondering, well, how do we know what this input and this input are? And really, you don't know, but the difference between a 1 and a 0 is a 1 is the presence of a voltage and a 0 is the absence of a voltage. So if we assume that this is the first time that we're turning something on, then it will have zeros in these spots because they won't have voltages at them to start with. So I'll just go in, I'll just label these zeros to start with, but that's just because we're assuming that we're going to turn it on, and that's kind of how you can start this process. So let's figure out how these signals propagate towards each other. So let's do this in red. So 1, 0 will give us a 1 out of here, and that 1 will carry down to here, making that a 1, and then that will make this a 1, and then that will make this a 1, and then that will make this a 0, and that will make this a 0, and that will leave this a 1, and we reach a steady state. And so what we'll notice is that the combination of 1, 0 made Q a 0. So we'll remember that. That means that probably 1, 0 will end up being reset because it made Q a 0. So let's try changing something and see what happens. So let's change B to a 1. So now that that's a 1, and this is a 0 from before. So 0 and 1, that will still produce a 1 out of here. And then this will be a 1, and then we'll notice that nothing changed. So when we went from 1, 0 to 1, 1, and there was no change, so we can call that hold. So 1, 1 will probably be hold, but let's make sure that if we go from 0, 1 to 1, 1, let's make sure that that one is also hold. So in order to do that, let's get ourselves to this 0, 1 state. So I'm going to do this in I guess blue is a good color. So we're going to change this 1 to a 0. So now we're going to be in the 0, 1 state. So 0, 1. So now we have 0 and a 1. That makes this a 1. And then this becomes a 1. And then this becomes a 0. And then this becomes a 0. And we reached another steady state. But this time, 0, 1 made Q a 1, which means that that one's going to be set. And to confirm that 1, 1 is hold, let's change this 0 up here to a 1. And when we change that to a 1, this one over here doesn't change, which means that nothing will end up changing. And so now we can confirm that 1, 1 is hold. So just for practice, here what I'm going to do is let's get this cleaned up a little bit up here. Let's erase some of this stuff. And then this one was a 1. So now let's, just for practice, let's go back to, so right now we have Q as a 1. So let's reset. So in order to reset, we have to go to state 1, 0. So let's change this 1 to a 0. And when we do that, if we look at our truth table, this 0 becomes a 1, which makes this a 1, which makes this a 0. And we'll notice that 0, 1 is in fact reset. We already knew that, but it's just good practice. So now let's go test this illegal state. The only option we have left is 0, 0. And so let's change this 1 to a 0. So let's just remove some of that. And we're going to change this to a 0. So now that this is 0, this output will become a 1. And then this is a 1, and then this is a 1. We'll get rid of that. And what we'll notice is now when we have 0, 0 put in, our outputs are the same. And so 0, 0 is illegal. So now all you have to do is literally just write these words down in the right spot. So like this would be illegal. And 0, 1 would be set. And then you just fill out the rest of this and show some work kind of like I did. And that's it. That's how you do the last problem.